Hello students, today we will continue our next topic regarding for the Raoult's law. It is very important topic on the basis of board point of view. One numerical comes from this topic. Okay. First of all, we have to understand what is vapor pressure. Let me explain you what is vapor pressure. Okay, students. Suppose I am taking the example. The proper definition you can understand from this example. Suppose taking the example, there is a water in this liquid, water in this container. Okay. After some time, vapor is generated over here. Vapor is over here. Vapor is over here. Okay. So what is vapor pressure? At equilibrium condition. What is equilibrium condition? The pressure is applied on the liquid, and the same pressure applied, the vapor is also applied the pressure on the liquid, and liquid is also applied the pressure. It is the equilibrium condition where the pressure is equal to the applied pressure by the liquid. So in this condition, the pressure contained this closed container. The first condition is, as you know, the equilibrium condition is that first of all the system should be in closed container, and second there should be equilibrium. After that it will be possible in equilibrium. In open container, as you know, equilibrium is not possible. Are you getting my point? What I am trying to say? So in this condition, the pressure applied in this container, it is called vapor pressure. For different liquids, suppose if the particles are more vaporized, vapor pressure is high. If particle is less vaporized, then vapor pressure is low. Are you getting my point? Next is the Raoult's law. Very important topic. Just understand your this topic. Okay, what is Raoult's law? First of all, what is volatile? Volatile liquid, the liquid or solute, solvent, whatever is that can be vaporized. Where volatile means vaporized. You have to learn in this way. Volatile means vaporized. For the solution, the volatile liquid, the partial pressure of each component in the solution directly proportional to the mole fraction of solution. What is partial pressure? The pressure is applied in this liquid. The pressure and partial pressure, you can say the partial pressure in this container is more directly proportional to the mole fraction. Okay, this one is a mole fraction. I am taking the example of mole fraction as in your book. It is generally depends on the solvent. X1 is a mole solvent over here, and if I am talking about the X2, which is a solute with the respect of your book, I am explaining in this way. P1 is a partial pressure directly proportional to the mole fraction. For a volatile condition should be volatile. If it is not volatile, the condition should be different. Okay, the partial pressure directly proportional to the mole fraction. I am explaining the derivation over here regarding for this derivation. X1 is a mole fraction of solvent. Suppose proportionate, if I remove the proportionality sign, it is like this. Partial pressure, it is with the respect of solution. Okay, proportional, if we remove the sign of partial pressure, the value is come P1 naught and X1. This one is a constant. I can say this one is a idle pressure. Let me explain you. P1 naught is a idle pressure. Idle pressure with the respect of solvent. Very important thing. Whenever I am talking about the idle pressure, it is always P1 naught, P naught. Whatever explain in your book, P1 naught or P sometimes. Okay, and P1 is a real pressure. Real pressure with the respect of solution. Okay, I am keeping this P1 upon P1 naught is equals to X1. Just keep this value in the upon. Okay. Next, I hope you write down this statement. I am further explaining this derivation. This is very important derivation from the board point of view. P1 upon P1 naught is equals to X1. Suppose P1 upon P1, I am subtracting both this value. 1 minus P1 upon P naught, P1 naught is equals to 1 minus X1. And as we know, X1 plus X2, as I have already explained you, X1 plus X2 is mole fraction is 1. It is like this. X1 plus X2 is mole fraction is like this. So you can understand by this in this method. I am writing over here that way you can easily see. X1 plus X2 is equals to 1. I am subtracting this value. P1 naught minus P1 upon P1 is equals to 1 minus x1. As we know, 1 minus x2 plus x1 plus x2 is equals to 1. So 1 minus x1 is a x2. So very important topic. What happens in this way? It is called relative lowering in vapor pressure. Very important topic from your textbook. This is called relative lowering. This one is a as a real pressure. Okay. Sorry, ideal pressure. This one is a real pressure. This one is a also real ideal pressure. Ideal minus real upon ideal. Relative. This thing is called relative lowering in vapor pressure. Write down in proper way. Relative heading is from a textbook. Relative lowering in vapor pressure. I am both the numerical portion explaining simultaneously. Relative lowering. Lowering. Suppose this is ideal. Lowering relative. Why it is called relative? Suppose I am giving an example. First chocolate value is 5 rupees, and next after lockdown it has a value of 6 rupees. So relative increment. So relative. I am taking the example reference of solvent. So this one is a solvent. This one is a solvent. This one is a solution. It is like this. Always put the values in this way. If you are not keeping this way, you have a problem with the relative lowering. If in the numerical, all the time question in different way. I will help you to. I will explain you some examples also. But this is called relative lowering vapor pressure. If in the example lowering vapor pressure, so this value is lowering in vapor pressure. Just read the question very carefully. Relative and lowering in vapor pressure. Vapor pressure. Okay, are you getting my point? Suppose x2 means, what is x2? N2 upon n1 plus n2. And I am putting this value if n2 is very less than n1. What happen? It is like this. Delta p. P naught minus p is a delta p over here. Delta p upon p1 naught. Yeah, delta p1 upon p1 naught. Relative lowering vapor pressure. If N2 is very less than, what happened? N2 upon N1. I am putting this in this way. W2 upon M2 and W1 upon M1. W2 is with the respect of solute, and M1 is respect to the solvent. This is the very important formula from your board point of view. Write down this one. Okay, students, as you know, the Dalton's law of partial pressure with the respect of gases as it is applies on the liquid state. What is the statement regarding for that? The total pressure over the solution phase in the container will be the sum of partial pressure of the component. Suppose I am taking example of in this way. P1 is equals to P1 naught x1, as we already discussed. Same as it is P2 is equals to P2 naught x2. Okay, are you getting my point? Here I am adding the sum. So P total is equals to P1 plus P2. As you know, we keep the value from this side. P total is equals to P1 naught x1 plus P2 naught x2. What is the statement? First of all, look at over here. The total pressure over the solution phase in the container will be the sum of partial pressure. This one is the first partial pressure, second partial pressure. The total is the always sum of their partial pressures. If there are 3 components, P1 plus P2 plus P3. If there are n components, P1 plus P2 plus P3 tends to Pn. So P total is equals to P1 naught x1, P2 naught x2. Are you getting my point? And as we know, if the 2 components are over here, as we know, x1 plus x2 is equals to 1. What happened regarding for this? P total is equals to, suppose if the x1 is missing, so we put the value P total is equals to P1 naught 1 minus x2 is equals to P2 naught x2. P2 naught x2. Are you getting my point? Suppose I am multiplying this. P total is equals to P1 naught minus P1 naught x2 plus P2 naught x2 over here. After the solving, P total is equals to P1 naught x2 and P2 naught. X2 is common. minus x2 is common over here, minus of x2 is common, suppose, okay, so the value is P1 minus P2 naught. Are you getting my point? P1 naught minus P2 naught. I hope you are getting. I am putting this value P1 naught 1 minus x2, P1 naught P1 x2, P1 naught x2 and P2. After that P1 naught is a common, suppose, and x2 is common in the here, x2 is come over here. Suppose P1 naught and P2 naught. Suppose if x2 is missing, we keep it 1 minus x1. So this is the final. Basically, the main formula is this. In your textbook, it is written like this. Don't get confused over here. You can apply it in this way also. There is no problem with that. So are you getting my Dalton's law? It's related from here I am explaining with the relation of Raoult's law. But Dalton's law, it relates from this way. Here there is a very important graph in your textbooks. Suppose I am rubbing this. I hope you will note down. Okay. Look at the graph. What is the explanation of the graph? Look at, very important. I am just writing the first equation over here. Suppose P total is equals to P1 naught x1 plus P2 naught x2, and x1, as we know, x1 plus x2 is equals to 1. Okay, look at over here. Suppose I am making the graph between the Weber pressure and mole fraction. Weber pressure, here the Weber pressure of P1 naught, P2 naught. So let me make a straight line. This one is a mole fraction in both sides. Okay, this one is a vapor pressure, this one is also vapor pressure, x1, this is called P1 naught. Okay, this is a P1 naught, this one is a, suppose P2 pressure is a high as compared, you can take any value of high, P2 naught. I am explaining according to your textbook. As we know, x1 plus x2, P1 naught x1, suppose here the value is x1 is equals to 1 and x2 is equals to 0. And here the x1 is equals to 0 and x2 is equals to, okay, look at over here very carefully. If x1 is a 1, it has a maximum value, this value will be 0. If x1 is a 1, so P total is equals to P1 naught x1. It relates from directly, it depends on one mole fraction if another mole fraction is 0. If any other molecule is absent, so it directly relates from this mole fraction. So the P1 is x1 is maximum over here. P1 naught is a, so this one is a 1. So P total, so P total is equals to P1 naught. As it decreases, it goes to that side. As it decreases, P2 value increases. As it decreases, x1 it moves towards to the x1 is there, so x1 is 0 over here, so it is decreases. You can't say this is increases. Let me make a straight line over here. Are you getting my point? What I am trying to say? Okay, so this value is a P1. P1 is equals to P1 naught x1. It relates in like this way. Here x1 is 0. Here x1 is 0 and x2 has a value of 1. X2 has a value of 1. So as it decreases, it is decreasing in this. The graph goes in this. P2 is equals to P2 x2. Okay, P2 x2. In this one, the graph is like this. And the total in overall value, we can make the peak to peak in this way. P total is equals to P1 plus P2. Are you getting my point? This one will increase, this one will decrease, and this one will increase, this one will increase, because x1 plus x2 is equals to 1. If this one is a 40, this one is 60. It always come in a 1. If this one is a 30, this one is 70. If this one is a 80, this one will be 20, because always it is a 100%. So the graph will be for x1 is a 1 over here and x2 is 0. As x1 decreases, it move towards P2. It move towards P2. Here x1 is 0, P total depends on the P2, because x2 is a maximum over here, and same as it is related from here. Are you getting my point? It is a very important graph as the board point of view. If you have to ask in the board exams, you have to make this diagram. Okay, I hope this point will be clear. Today's lecture will be end. Thank you so much. All the best.